guys, Nick here again. So by now in this tutorial series you should have some crates or static meshes that you've converted into K-actors, and you should have them starting to appear like they're floating within your water environment here. However, there's a couple of limitations with the way that we've set up our buoyancy, or how we're faking buoyancy in this scene. I'll just jump in and play and explain what those are. Okay, so the first thing, and you probably noticed this with your scene as well, is that while we've got our crates bobbing up and down, which is the effect that we wanted out of the this cylindrical force actor, the main issue is, particularly with mine here, they're bobbing way too much, which is creating an unrealistic effect. The other issue that we have is that there's no dampening whatsoever. So these will continue to bob and they will never lose momentum, which we know is incredibly unrealistic. If you were to drop something buoyant in water, it would probably go underneath the surface, pop back up, go underneath again, and pop back up until it would actually reach a level of equilibrium and start to even out. We don't have that, so that's a big problem. The one of the other problems we have, and I'll just jump in and shoot a crate so I can demonstrate this. Okay, so shooting the crate on the corner or applying an impulse to it will put it into a spin, and it will always spin at the same rate until it runs into something. There's no damping whatsoever on the rotation of the object. There's also no linear damping as well. So when we kind of shoot it across the surface of the water, it never loses momentum. So we've got a couple of issues there, which is basically making our floating effect quite unrealistic. So we're going to address those in this video and try to get some better physics effects in our scene. So the first thing I'm going to do is I'm going to have a look at fixing the issue where the crates are bobbing too much within the cylindrical force actor. So we're going to go to our content browser, go across to our scene tab to find our cylindrical force actor. And as I explained before, I like to use the scene tab on smaller scenes just because everything's quite manageable. On large scenes, it can be a bit tricky to find stuff in this list. Okay, so really the only thing I'm going to affect here is going to be the lift strength of the cylindrical force actor. So I actually want my crates to bob less, and it might seem a bit counterintuitive for me to raise the lift strength in order to get that effect, but that's actually exactly what I'm going to do. So at the moment, at 1000 it was bobbing too much. If I bring it up to 1300, the theory behind this is that when we converted our static meshes into K-actors, they got a default physical material applied to them, and that is they got their own density, they get gravity applied to them and things like that. So when they're made live in the world, they will begin to fall, and we've already seen that happen. Now the cylindrical force actor has to catch them before it can kind of bring them back up. So if I raise my lift strength, that means my force actor is going to catch that barrel quicker. It's not going to allow it to fall so far down into the volume before it brings it back up. So hopefully this should give us a more subtle kind of bobbing effect. So just a value of 1300 in there. And of course, bear in mind your values will be different because your scene most likely will be quite different to mine. So 1300 in there. Let's jump in and play and see if we've got a better effect on the actual ambient bobbing of the crates. Okay, so instantly that looks a lot better. They're not kind of going all the way under and all the way back up like they were before. It's nice and subtle, but we're still left with the problem that they never lose momentum. So even though it's a better look at the moment, it's still unrealistic. We need them to kind of come to an equilibrium at some point. So the way we're going to start to do that is to have a look at physical materials and also a bit of rigid body damping in the actual water volume itself. So first thing we'll have a look at is the physical materials. So as I said before, when you convert a static mesh that has collision into a K-actor, it gets a default physical material applied to it, which has a whole bunch of default properties. One default property is the density of the object, and basically it determines that based on the collision bounding box of the object, and this is why K-actors need collision. Now that can be okay in certain instances. Generally speaking, you know, some things that are smaller will want to be lighter, and things that are larger will want to be heavier. But not in every instance. We might have a hot air balloon, for example, and we don't want that hot air balloon to be super, super heavy. So we would need to create a physical material override to tell it that even though it's large, we want it to be light. So that's what we're going to do now. So if we go back into our content browser, and I'm just going to right click on some gray space here, but you could also come down and hit the new button down here to create a new asset. I like the right click. That's just me. So we're going to go a new physical material. I'm going to save it into my package. You, however, should be saving it into whichever package is housing all of your assets for your fluid environment scene. Now I'm going to call this M underscore, which tells me it is a material of some type, even though it's a physical material. I'm going to call it something incredibly descriptive, so it's very easy to find. So let's call this crates phys mat, which tells me, of course, that it's a physical material for our crates, and it's coming out of the physical material factory, which is exactly what we want. Hit OK, and we're going to get a bunch of properties show up. Now, we don't really need to do anything with these properties at the moment. Don't close your content browser, by the way. I'm just moving mine slightly off screen. But at least this tells us what K-actors what properties get applied to K-actors as default, is exactly what will happen when you create a new physical material. Now, it's not going to do anything by itself, so we actually need to apply it as an override to one or all of our K-actors. Now, I'm just going to use one as an example so that we can kind of, I guess, see the difference between a crate that has an override and a crate that doesn't. So on my first crate here, I'm just going to select it. I'm going to hit F4 to bring up the properties of that K-actor. And in the search bar here, I'm just going to do a search for PHYS. And I can see here under Dynamic SM Actor, Static Mesh Component, Physics, I have a Phys Material Override. Here's where we're going to override the default physical material with our new one that we've just created. So with your content browser, you should still have your physical material that you just created still selected and visible. If it's not, you're going to have to go up on here and do a bit of a search and see if you can find it. Now, with that selected, and you can tell it's selected because we have the yellow bounding box, I'm going to go back to my K-actor properties, hit the little green button here to punch it in, to tell it use this physical material instead of the one that you're using by default. Easy as that. We now have a physical material override on that K-actor only. So I'm just going to minimize my content browser here. And yeah, no, we don't need to do anything else with the properties of the K-actor, so we can close that as well. And I've still got my physical material properties open here. So what I'm going to do here is just go through and chat about some of the properties in here which are going to be most important to you for this particular scene. There's a bunch of properties here which are incredibly important for physical materials in general that I'm not really going to be able to touch on in this series. So I would highly recommend that you go to the Unreal Developers Network and do a bit of your own research on physical materials so you can have a look at some of these impact and slide effects, which are super cool. But as I said, don't really relate to this tutorial series, so I won't be going over them. So let me just grab this, move him a little bit. Okay, so the first thing probably to go through is, as I was mentioning before, is your density. So density is going to control effectively the weight or the mass of that K-actor within the environment. So at a density of 1, that means it weighs as much as its weighs, how am I going to say this? It weighs as much as it is large, I guess. I don't know. But basically that just means if it's set to 1, it means, okay, it's using the default. It's taking the collision bounding box and it's saying, okay, this is how heavy I think it should be based on how big it is. Now with this number, if we actually want that to be half as heavy, we can literally halve it. We can go 0.5. If we want it to be twice as heavy, we can give it a value of 2, so on and so forth. So I'll just do that now and give this a value of 2. Actually, I'll just do put it back in line so we can see the effect. That's still set to 2, which is good. All right, I'll jump in and play, and we should see that this crate will sink a lot further than the others before it gets brought up because we've given it that extra mass. Yay. That totally worked. Of course I knew it would. So that's your density. So it relates to the mass or the weight of the object in the world. So I'm just going to set that back to 1, just default, because I'm actually pretty happy with the way they're weighted at the moment. Now another property which is sort of pretty important, not so much within the water volume itself, but when your K-actors are colliding, let's say with another surface or something like that, you've got your friction. So if we reduce our friction, let me bring this over land so we can get some demos going. Friction is basically what it says it is. So if we reduce the friction of an object, it will slide across surfaces. Now, if we have a high friction, it will generally stick, and then if there's enough gravity, it will want to stick and roll basically. So just excuse me while I kind of get this into a position where I might be able to kind of get a bit of a slide happening. A little bit of rotation here. Nope. Yep. Okay. All right, now I'm just going to reduce the friction to 0, so there'll be no friction whatsoever. So it should basically wake on level start, fall, and then we should see it slide. It shouldn't attempt to stick to the terrain at all. So I'm just going to right click and play from here to check that out. Yeah, so we can see very slidey. Away she goes. Okay, so no friction whatsoever, and yeah, even as it passes through the volume, there's no friction because we haven't applied any rigid body dampening there, which we will in a second. Now, alternatively, let's see what it looks like with a lot of friction. So, I don't know, let's throw values in. Let's go 3, see what that does. Okay, way too much friction, so it can't even continue along the surface because it's stuck. It literally has got stuck. Bring our friction down to default. Default is 0.7, but 0.5 will do it. And we can see, yeah, there's a little bit of friction, but still not a whole lot. So there you go. That's your friction property there. Now another fun one, and one again, particularly more for colliding with surfaces and things like that. I'm not going to get that back. That'll do. Let's get it relatively straight. Okay, so the next one is restitution. An easy way to think about restitution is that it will control effectively how bouncy your object is. But when we talk about bounciness, it actually relates to energy. So if you have a restitution of 1, it basically means that when this actor wakes and then falls and drops, it will hit and collide with the surface below, and then it should get the same amount of energy back in a bounce. Now that's if it's set to 1. So 1 essentially is equal. So the amount of force going down, it gets all that energy back to come back up. You can of course go more. You could set that to 2, and then, you know, hypothetically, the object would get twice as much energy back. It would bounce higher than the amount it has fallen. Alternatively, you know, you can have something less, which means that the object will hit and then it will only bounce back up to half height or something like that. So let's give this a really high restitution just to see what kind of effect we get. It might be a bit odd with this in this example, just because it's a crate, it's a cube, and we're kind of hitting on a slope. We might not really get the desired effect for the example, but hopefully it should be very bouncy. So let's have a look. Yeah, very bouncy. And you also would have noticed as it was falling very, 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 very slow. That's going to be A, to do with the density, as we discussed before. And there is another thing which will affect that, which will be the linear damping, but we'll go over that in just a second. So that's your restitution or bounciness. I'm just going to set that back to default, which I think was 0.3. I think, and leave him there, that's fine. All right, now for this example, we're going to go through angular damping now. I'll just put my crate back in the water. It's going to be the easiest way to show this. All right, is that in? No, it's under. Yep. Okay, that's fine. All right. So one thing, as I explained before, when I was shooting the crates, we were able to put them in a spin into a rotation, and they would rotate at the same rate forever. So that's where our angular damping comes in. Damping basically is just a way of curbing momentum and things like that on effects. So with our angular damping, it controls the how much the rotation of the object is dampened. So as default, we can see it's set to 0. Makes sense because it wasn't slowing down. So let's up our angular damping. Let's say something like 0.5, and we'll see if we can get that that spin to stop a little bit more realistically. So I might approach this from this side. Okay, so I'm just going to shoot it on the corner to get it into a spin. Say this corner, why not? Okay, so you can see it's come to a rest eventually, well, kind of, but yeah, the idea is that it won't go on and spin forever, which is obviously much more realistic. So that's your angular damping. So you can play around with that, and of course, a lot of these values, it's going to take a lot of tweaking to get something that looks, you know, I guess realistic or within the realms of what we'd, you know, what Earth physics would be or something like that. But that's half the fun, is playing around with it and getting your scene to be where you want it to be. I'll leave that angular damping on, actually, that's not too bad, at 0.5. Now, as I discussed before with your linear damping is actually different from friction in so much that friction more, we talk about friction more in terms of the object colliding or interacting with another surface. When it comes to linear damping, this is actually more like drag or atmospheric drag. So this is basically like if you were to drop something, you know, from a great height or something like that, would there be any drag on the object? Would it begin to slow down, or would it just continue at the same rate, or would it, you know, would it accelerate, I guess, if we had that as a negative? So I'm just going to up this linear damping. We can see at the moment it's set to something quite low, 0.01. So I might just up that. Let's up it to 0.1, which is probably going to be a fairly extreme example, but see what happens. Now, what I'm thinking is going to happen is if I come in and try to shoot this crate or give it an impulse in a direct line, we should see it not carry on forever and ever and ever, but we should see it start to slow down a little bit using the natural kind of drag, but that's still not the full effect, and that's where we get into rigid body damping, which is coming next. So I'll just move these slightly out of the way. We'll jump in and see the effect of our linear damping. So I'm going to attempt to shoot this in a relatively straight line. I've got a bit of room here. Okay. So it is damping, just not a whole lot. That's because we're still dealing in quite low values there. So we'll just up that, see if we can get a better example. Let's put it all the way to 1, which is probably going to mean that it's not going to go anywhere, but we'll find out. Again, I'll just get around this side. Okay, so we can see now it's very hard for me to get that moving because of the linear damping. Hooray! I've literally no idea why I just had to swim out of that volume then. I could have just hit escape. Oh well, anyway. So I'm going to actually put that back to what it was at 0.01, because as I said, that's affected by a bunch of things. Because we're floating in a volume here, our atmospheric drag or linear damping becomes a bit of a weird one. In this instance, we would, to get the objects to kind of slow down, I guess, as they're entering the water from outside the water, we need to look at rigid body damping, which is in the UT water volume itself. So I'm just going to close down these physical materials now. Oh, UDK had a bit of a stutter. Grab this crate again, and I'm just going to drag it. Just going to drag it over my landscape again. And what I want to kind of show here is how we can affect what happens between the outside environment and the inside environment. So if a K-actor is moving from outside to inside, how we can actually make that seem realistic and not make it seem like they're all part of the same environment. So in order to do that, we're going to go to our content browser again, and mine is minimized. Across to our scene tab, identify and find our UT water volume, and within here I'm going to do a search for rigid, and we can see here under the physics volume component, rigid body damping, and of course it's set to 0. So as some of you may have noticed, if you've been putting your K-actors outside and trying to shoot them inside, it doesn't look like they're going into water. We know when things hit water, they will slow down a lot. That's not happening at the moment. So we'll put a few different values in here just so we can see what's happening. So at 0, we know nothing is going to happen. It's going to slide down the hill, it's going to hit the water, and just keep going, as it always has. So let's put in a value of something super, super extreme. I'm going to put in a value of 200. Now, I theorize that with this, the object should, when it tries to enter the water, that it won't actually even be able to enter the water at all, because it will be dampened so hard that it loses all momentum. But that's the theory. So let's get somewhere decent and have a look. Okay, slidey, slidey, slide. Nope. There you go. So it's still, you can see now it's dampened now, but you can see it had that momentum and it was like, oh, let me get in, but it couldn't because it was being dampened way too much. So let's put something a little bit more realistic and see how that affects it. So back to content browser, back to scene, back to UT water volume. And again, just the main reason I kind of like to do things here, particularly with volumes, because they appear in game as generally as wireframes, they can be really difficult to select, particularly when you have a lot of other things in the way, like your landscapes, etc. So I just like to go in here. Now, again, I'm just going to do that search for rigid. We're going to give this a value of, let's give it a value of 2.5, which is obviously much less than our stupidly extreme example. And again, let's have a look. And now the idea is it should be able to enter the water volume, but it will lose momentum as it enters and then begin to float. So let's check that out. Let's right click and play from here. Maybe not enough momentum for this example, but it's working. Okay, so we can see it's just sort of slid into the volume and then it's been dampened. So it can't go any further. What I might try is I'm actually going to put this on a more on a steeper slope, just so we can get a bit more. Actually, we don't need to do that. What am I doing? I'll just shoot it. That's what we do with problems. Okay, so probably too much damping for a realistic effect here. So I'm going to reduce that again. So there is a lot of fiddling, as I said, to be done here. Back to the UT water volume, do another search for rigid. I might put that on something like 0.75, and I think that might be a slightly better damping. Okay, so we can see it's maintained momentum and then dampened. See, to me that's not too bad, but of course that's only one case. You'd have a lot of cases in your scene to check this on. So, and even when we go in, we can see that it has completely stopped moving. So it's come to the point where it has been completely dampened. And we can see with our other crates as well that they've been completely dampened. So I mean, depending on the scene and depending on what you want to do, that may or may not be the right kind of effect for you. I mean, I guess ideally you would want some kind of ambient movement, but it's just going to be a play around essentially between those three things. So we'll go through and we'll do a quick recap of everything that we've had a look at in this tube to try to get our physics effects looking a bit better. So the first thing we did was in our cylindrical force actor, where we affected the lift strength, which again is the play between how much the K-actor has been lifted upwards in that volume and how much natural, I guess, force is being applied to it by its own gravity and its own weight in the world. So it's going to be a bit of a play between your lift strength here and the natural density or the density you set in your physical material override. Which brings us on to the next thing we looked at, which was our physical material override. So with that K-actor, again, I'll just do a search for phys and find it. I'll find that in the content browser, bring up its properties again. So there we have our physical material override, and we went through and we discussed friction, which is basically friction when it comes to colliding with other surfaces. Restitution, which is your bounciness or how much energy the object gets back when it collides. Angular damping, which is damping of the rotation of the object. Linear damping, which is damping of in a linear fashion, so generally speaking, drag in the environment. And density. I'm not sure if I've already said that, but yeah, density, which is where we actually control the weight or the mass of the object. And then the very last thing we did was in our UT water volume under rigid body damping. So that's it, guys. Hopefully now you should have some slightly more realistic physics effects if you're going for a realistic kind of thing. Obviously, if you're on the moon or something, you would have very, very different physics settings. But in this scene, which is kind of Earth-like, kind of earthy, these are kind of appropriate. So there you have it. After this tutorial, I'm going to go on and make a advanced water material just to get a few extra things happening in the actual look of our water. In particular, real-time reflections as opposed to cube map reflections. So look forward to that one, and I'll see you guys in the next tube. Thanks very much. Bye.